9:30. Let's get started, please. Welcome to the last lecture of algorithms and data structures. I already know in advance that there's a bit too much stuff packed into this lecture, so the pace may be a little unreasonable, but I will do my best. So the first thing we need to do is some things we didn't finish from last class, so I'm just going to jump back to lecture 7 for a minute. And scroll way down here. Okay, so first thing, I posted about this in a GitHub issue, but I added some things here about setting up the objective function. So this was the code I showed you on Tuesday. I just unraveled the double loop comprehension thingy into the exact same code that's easier to read. So that's this thing here that I'm calling approach number 2. And then I also added this third thing, which is actually the most relevant for the lab and the way you're going to set it up in the lab, which is that another way you could think about the objective is the sum over that whole table. Remember, we had that table of TAs and courses 0s and 1s. The sum of that whole table of the enthusiasm at that spot multiplied by x at that spot. And the trick is that we just want the enthusiasm of the cases where TAs are actually assigned. And when x is 0 and you multiply 0 by something, it just goes away. And when you multiply 1 by something, it just stays the same. So by doing the sum of enthusiasm multiplied by x over the entire table, because x is either 0 or 1, it's just picking out the cases where x is 1 and basically adding those up. And then you have the enthusiasm for just the cases where the TAs are actually assigned, and you basically add up the total enthusiasm. So in lab, you're going to do something very similar. You have this energy score that you want to minimize, and then you have this table of 0s and 1s again, and you can do the same multiplication trick, and basically when x is 0, it's going to multiply the energy by 0, and when x is 1, it's going to multiply the energy by 1, and then when you sum over everything, you just end up with the total energy of the 1s, which is exactly what you want. So take a look at this when you're working on your lab. We did this last time. Oh yeah, another thing I wanted to say, I posted this on Slack already, but when we did this by hand on the board, last time I actually made a mistake. I assigned, I think it was Alice to 542 or something like that, but that actually wasn't possible. So I was actually hoping for me to fail horribly when I did it on the board last time to more motivate the code, but I accidentally made it easier than it really was. Anyways, okay, so printing out the results, we looked at this last time. How did this work? Yeah, so we don't really have time to say much about how it worked, but just a little bit of intuition about, so this is called linear programming. It's because the objectives and constraints are linear functions of x. If we don't really need to go into that, or we don't really have time to go into that, but basically you can only use pulp to solve a particular type of problem, and this problem happens to be of that flavor, and the problem in the lab happens to be of that flavor, but it's not actually that easy necessarily to figure out if your problem has that flavor, and it's a bit beyond the scope of the course. So if you're interested, you can ask me. But basically, just to give you a bit of intuition, that for example, I said last time if you've assigned a TA to 2 courses in a block, well, that's not allowed. So it doesn't need to try all possibilities with that, because it already knows that's not allowed. But not only that, it doesn't need to try assigning a TA to 3 courses or 4 courses in a block. So it basically knows something about the structure. When you say less than or equal to in a constraint, if that constraint's violated, you know to not make it even more violated. So the solver actually knows something about the problem that allows it to be super fast at solving the problem. So on the other hand, with the strings we had before, A, 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 B, 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 the thing is, the only thing we provided it was a function that took in one of those strings and said, did it violate the constraint or not? So it had no way of knowing that A, B, 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 that was not allowed because you're not allowed 3 A's, but it would still try every other combination with 3 A's because it didn't know really what the constraint was. You only just gave it the ability to check for a given string, did it violate the constraint or not? And so you end up just having to try everything. Okay. Yeah, we can skip that. I just wanted to say one quick thing was The problem we did here in lecture is basically actually 3 separate optimization problems, block 1, block 2, and block 3. And you could do those totally separate from each other if you wanted to. In the real MDSTA thing, it's a little more complicated than that because, for example, some TAs will say, I insist on doing all 3 blocks or I don't want to be involved at all. And so if you have constraints like that, then the blocks actually affect each other because if you want to use a TA in block 1, you have to also use them in block 2 and block 3, and the blocks get entangled with each other, which is not true in this more toy version. Okay, so yes, I basically wanted to say there's a whole bunch of types of optimization problems, and pulp just solves a certain subset of those problems, and you can read more about this later. But the real key here is that you kind of want to match your type of problem to the way of solving it, and maybe some problems can only be solved with brute force. Some problems you can do something better, as you're going to see in lab. So that was an extremely rushed finishing off of last class. Are there any questions about that before we start today's class? Okay, let us start today's class. So today we have a bunch of stuff to do, but really 2 main things, dynamic programming and vectorization. And then some optional things that hopefully we'll get to, but they're not on the lab or the quiz, but I would still really like you to know about them. Okay, first thing, caching and memoization. So we actually talked about the Fibonacci numbers before when we talked about recursion. And again, this is a sequence where each number is the sum of the previous 2. So here is an implementation of this. I'm creating an array, so I want to get all these numbers up to the nth number. I'm creating an array, and I just loop and say element number 2 is the sum of element number 0 and element number 1. Then element number 3 is the sum of element number 2 and 1, and so on. And this code works just fine. And then we had this recursive version that I showed you a few times ago, which is not a good example of recursion, as we talked about last time, because, well, the code looks nice, but it's very slow. So for example, if I call this, it works. But if I time both of them, I get 50 microseconds versus 5 seconds. So whatever that is, 100,000 times slower or something like that. And we talked about it back when we talked about recursion. This is, calling this whole tree of function calls, which turns out to be unnecessary in this case because you can just store things as you go along. So, we did this last time. Yeah. I think we mapped it out last time. Okay, so the problem is repeated computation. So, for example, fib of 33 is called by fib of 34 and fib of 35. So fib of 33 is computed twice for no reason, because you did all that work. You might as well just remember what the answer was rather than doing it again. And like fib of 10 is called a bajillion times by so many branches of the tree. And so it's just pointless to spend 2 to the n-ish amount of effort to do this thing that should only take linear time. So there's something called caching, which refers to basically storing something and saving it for later because you might need it later. And then memoization is a specific case where we're doing that for function calls. So I've posted a link here. But Python has this really neat thing, this caching decorator. So the @ sign and then some stuff before a function, that's called a decorator. We haven't actually talked about those in this program, but that's not really important for what we want to talk about today. Just I can do this thing to my function. And basically what this says is, okay, modify this function so that whenever you call the function, just remember what the inputs and outputs were. Someone called fib of 35 and the result was whatever. Okay, just store that, and if someone calls fib of 35 again, just check, hey, has that happened before? And if it's in my cache, just return the answer that you remembered instead of doing all that work over and over again. So don't worry about the syntax because you haven't seen this before. But the idea is just remember what you did. And if you call the function with the exact same arguments again, just look it up first. And so what we see here is that now it's back in the microseconds and maybe even around the same speed as what we had before, instead of taking whatever it was, 100,000 times longer. So this is still the recursive implementation, but we just added that one line at the top, and it's just saying, remember what you did and don't recompute things. And now it behaves kind of reasonably. Jerome.
So does it only store fib of 35 and not all of the recursive calls that it first?
It stores all of them, but so it's basically making a table that says, n and fib of n, and then it calls, I don't know, 33, and it's some number, and it stores that number. And then, but the thing is, if someone calls fib of 33 again, it doesn't make another entry in the table. It just looks this up and returns the table. So at the end, your table is only going to have 35 entries in it, basically, because it'll have 35, 34, 33. So in this case, the size of the table is not going to explode. But that is a concern with this in some cases, that if you're calling it with different things every time, it might take up too much memory. So it's a kind of a memory for speed trade-off. Okay, so this cache thing is built into Python. It's kind of a nice thing to have. There's also some third-party packages like joblib that can also do this type of memoization. That's pretty much the same thing. In the cache, it's storing it in memory. With joblib, it's actually storing it in a file, so you could have a really big cache. So I think this should also work. Yeah, so you don't need to memorize the syntax. You may never even use it again. I'm not sure, but I want you to understand this idea of caching and memoization, and that in some cases it's a good concept to have handy in terms of remembering your function calls. And will be useful when we talk about dynamic programming, which we are now about to do. Okay, so here's our motivating example for dynamic programming. You've probably seen things like this in GitHub all the time. So you make a change or you make a commit, and then GitHub renders this red and green thing for you that basically shows you what change you made. So my original text said, well, this is a demonstration of diffs in GitHub. Let's see if it works. And then what did I change? I added 3 spaces here. I capitalized the word C, and I deleted the exclamation mark. So the question is, how does Git or GitHub compute this thing? How does it decide what to highlight in red and what to highlight in green? And first, actually, I have to convince you this is a pretty hard problem, because maybe for a human it looks easy. But first, I'll convince you it's quite a hard problem, and then we'll talk about how to solve it efficiently. Okay, so yeah, the general idea is it's highlighting characters that are different from the other version, or not present in the other version. And here's the thing. You could just say, well, here's the change I made here. I deleted the entire original version and added the entire new version. I guess that could be a valid thing, right? Because if you delete the entire original version and add the entire new version, that does get you to where you ended up. But that would not be useful for us humans trying to read this thing, because just everything would be highlighted all the time, and we wouldn't actually learn anything about the changes we made. So it's not OK to just have a highlighting that is correct. But actually, there is an optimization problem being solved here, is that we want to highlight as few characters as possible. It's uninteresting. It's correct, but uninteresting to just highlight everything. Okay, so yeah, so we have an optimization problem. So here, for example, if our objective function is the number of things we highlighted, here we highlighted 4 characters in red and 6 characters in green. So we highlighted 10 characters in total. So we could say our objective function score here was 10. And in this case, that's the minimum you could have highlighted. And of course, you could highlight extra things for no reason, but that would just give you a worse value of the objective function. Any questions about this diffing as an optimization problem? Okay, here we go. So here is one of the key insights for this. What we're actually doing is we're actually doing an alignment. That is the best way to think about this optimization problem. So essentially, let's think about it like this. We added those 3 green spaces there, but if you kind of say, hey, those 3 green spaces were added, so if you remove them back out and shift everything over, you're kind of lining up the string. So the problem is, you don't want to think, if you just look at them the way they are and you say, oh, well, this I is different from this space, so I'm going to highlight them. This S is different from this space, so I'm going to highlight them. These are the same. This A is different, I'm going to highlight them. These are different, highlight. These are different, highlight. These are different, highlight. Then you're going to get into a mess, right? That's exactly what we don't want to do. So in fact, when characters are being added or deleted on one side or the other, we want our algorithm to actually figure that out, to say, oh, we added characters over here, and then we can line up the rest of the strings, and we can actually learn that, well, this D is the same as this D, and this E is the same as this E, and this M is the same as this M. So our algorithm actually needs to be smart enough to figure out that the strings are being shifted when characters are being added and removed, so that they don't highlight the word demonstration, even though when we look at it right now, the way they're lined up right now in position number 12, there's not the same letter. In position number 13, they're not the same letter, but they're not highlighted because it has figured out that they really are the same letter. So that's why this highlighting of spaces is so important, because it's saying, hey, these characters got inserted here, and now let's continue lining things up after that. So that's what I mean when I say we're looking for an alignment. And the problem is that what this means is we can't just go letter by letter and like I said, say, should I highlight this, should I highlight this? Because as soon as I highlight that space, it shifts everything and basically affects all the highlighting later on, because I'm saying everything got shifted over. So that's essentially what makes the problem so complicated, is you can't just go one character at a time. You have to think about the whole effect. And so what you really need to do is think about all possible highlightings or all possible alignments and say which one is globally the best, because maybe I add some things over here, that'll mean less highlighting way over there. And now we're into one of those horrible problems where there's all possible combinations of something and we can start to despair, and then we can be rescued by some kind of clever algorithm like what we saw earlier this week. So any questions about why this is a hard problem? Yeah, Aman. Oh, sorry. Sorry. Yes. Aman's right next to you. A bit louder?
Can't we loop through Google string and check the value of each character, and then if I find some change in the other string, then I shift on that loop and on this?
Aha, yes, the question is, can't we just loop through it, and if I find a change, can't I just shift it? Great point, but the entire point is you're doing what you said, Saurav, you're looping, oh, I and space, those are different. But which one do you shift? That's the decision you have to make. Because I could say, oh, there's a new character I, and shift that got deleted, and shift one string. Or I could say there's a new character space that got added, and shift the other string. And one of those is going to totally mess up the alignment later on. And so that's a kind of binary decision I have to make when I see a mismatch. Is, do I shift this way? Was it an addition of a space or was it a deletion of an I? And if you follow the deletion of the I path, it is going to be a disaster. And the only way you're going to recover from that to get them realigned is by adding a bunch of extra green highlights later to get them back aligned, and that'll give you more highlights in total for no reason. Yeah, so it's really, you're marching along, everything's good as long as they're matching, you're right. But as soon as there's a mismatch, you have this binary decision to make, and that's this exponential explosion of possibilities. And then you could go this way, there's another mismatch, another binary decision you have to make, and you get this kind of exponential sized tree of possibilities, which is what makes this a hard problem. Other questions? Tom.
What's the clever algorithm that's going to fail?
Okay, well, what's the clever algorithm? We're going to get there. Okay, so first, the not clever version. So this is the recursive solution that says the following. So scrolling up for a minute. Num diffs rec, it returns the number of characters in the diff between x and y. So here's what it does. If you have a match, so if the first characters are the same, then you can just recursively call yourself on the rest of the string, ignoring the first character. Because if the first characters match, you don't need to highlight anything. So we'll just go on to the next character. If you have a mismatch, that's down here, then you have two possibilities. And that exactly goes to the discussion we just had with Saurav. Either I can shift x, which means align the entire y string with the first character of x deleted. That's what this option is. Or I can shift it the other way and align the entire x string with just the rest of the y string. So that's an insertion of a new character. And then I want to take the minimum because whichever of these ends up having a small, and this is kind of the recursion reasoning that we have, whichever one ends up being smaller, that's going to be the better one. And then I need to add 1 to pay the penalty right now. So this is the slow version, the recursive Fibonacci, the recursive seam carving from your lab. We saw a bunch of cases like this. This is the try all possibilities version, but there's going to be kind of a 2 to the power of something going on here because I keep branching and branching and branching at my two possibilities. Is it a deletion, a red highlight, or is it an insertion, a green highlight? Questions? Victor?
And if we change one character, as we saw that we put in how do you say basically? In lowercase or uppercase?
Oh, right. Yeah. Okay, so
Yeah, sorry.
scrolling back up. So this, this is basically a change rather than an insertion or deletion, but what's going to happen in the code is basically going to do an insertion and then a deletion or vice versa. So both of them end up getting highlighted. So either it'll pick this branch and immediately that branch, or that branch and immediately this branch, it doesn't matter, but it'll end up highlighting both of them, and then you'll kind of get into the same level of alignment, but with both of them highlighted, and so you'll pay that penalty twice because you highlighted the red and the green.
Okay, but it doesn't look for it like...
Yeah, we don't need a special case. We could add a special case to say if, but we're just not worrying about that. We're just treating a change as an insertion and a deletion and highlighting both of them. So that's why we don't have to worry about that case. Carrie.
What if you insert more characters than already exist? Wouldn't that break down?
Right. What if you insert more characters than already exist? So going back down here, just looking at the base case, this is kind of what you're asking. So as you're going along, if you reach the end of one of them, like reaching the end of x, length of x is 0, that's basically saying just highlight all the rest of y because there's just more stuff in y. And so it's returning the length of y. That's basically meaning paying a penalty of 1 for each remaining character in y because we're going to have to highlight all that extra stuff. So yeah, if you just add 10 characters at the end, you're going to highlight all those 10 characters, and it's going to be through this base case. Yes?
What if you add them in the middle?
Yes. What if you add them in the middle? Well, that's the thing. It's exploring all possible highlightings. There's so many of them, it's hard to comprehend. But the best one is going to end up being highlight those 10 things in the middle so that the alignment continues properly after that. And it will figure that out because just considering all possible highlightings. So it's trying all possible things, but it'll say, this is an insertion followed by another insertion followed by another insertion followed by another insertion. It'll keep highlighting those 10 things you added in the middle, and then it'll get back to x equals y, x equals y, x equals y, x equals y, and so the score will just be 10 because you had those 10 insertions in the middle. You don't seem convinced.
No.
Okay, well, let's keep going. Alistair?
Yeah, so the changes we've been talking about have been kind of small, like changing one word, one letter. What happens if you write a new sentence, but it has spaces and the word the and things like that? Will it say everything's new, or will it say some of it's new or not?
Well, it's just going to find the minimal possible highlighting. So yeah, if you have A, B, C, D, E, F, G, and then A, B, C, here is new stuff, D, E, F, G, which I think is what both of you are asking. The best thing it's going to do is going to highlight, here is new stuff, and it's going to say this ABC matches this ABC, this DEFG matches this DEFG, and so you're just going to pay the price for highlighting all of these things. Annie?
But if there was like ABC here, D is new stuff, D, E, F, G, would it?
You're right. Okay. So, very good point. So you're right. Actually, if you had a D in here, the solution is not going to be unique because this highlighting of however many characters this is, 15 characters, is just equally good as highlighting these and highlighting these and highlighting this D, because they're both the same number of highlighting characters, so we don't know which one it's going to pick. It's just going to arbitrarily pick. Those two things were equally good with this D highlight or that D highlight. In our minds, we probably prefer this D highlighted, but we haven't encoded that in our optimization problem, so those will both be solutions. Carrie, you're good? Okay. Okay, let's keep going.
No.
All right, so I can call this function. Oops, I have to run the function as usual. I can call this function, and it's going to tell me, it's just going to return an integer with the score. So for example, here I added these two x's. They're going to be highlighted. I added that x over there. Gosh, sorry. I deleted these two x's from the input string and added this x to the output string, and so I have a score of 3. My highlighting is going to be all those 3 x's. Okay, so this code so far just returns the score. It doesn't actually return which characters are highlighted. We'll get to that in a minute, but so far we're just returning the score. Okay, how does this work? So I guess we already talked about this stuff through the Q&A, so let me keep going. So how slow is this code? I'm going to run it for the string. This will be slow. Yeah, right. So it shouldn't, this will be slow. Yeah, right. Those are very small strings. They're only length like 10 to the 15. And this is running right now, by the way, as you can see. So if this is slow, then the recursive thing is completely useless because you have to diff large files of code and stuff. And okay, not a shocker, right? The recursive thing is kind of the straw man implementation that it's not supposed to be good. It's just supposed to be kind of intuitive, and we want to find something faster. So it's still going, just for these tiny little strings. Well, I don't have all day here. Hope it finishes soon.
It won't.
It won't? Well,
No, it took a while.
took a while. Okay. Why is this? Oh, there we go. Okay. 50 seconds. So totally unacceptable performance for these tiny strings. So why is the code so slow? Basically the same issue we saw with the Fibonacci numbers is that it turns out there's a bunch of repeated computations in here. So we're having things where we keep getting back to where we started and kind of doing it all over again recursively. So for example, I could add something and then delete it, or I could delete something and then add it. but those are two separate paths in my recursion tree that are going to do all the other recursive calls the same, even though I'm really at the same place. And so there is hope here that maybe we can do something better because there's a lot of repeated computations going on here, like with Fibonacci. So we could try the memoization thing, but that's not that great because we don't exactly know how much memory it will take. We don't know how long it's going to run. It's kind of this weird thing that we're just tacking onto our function, but we can actually implement it from scratch in a way that we can really understand what's going on with our code. So here you go, Tom, the moment you've been waiting for. Dynamic programming. So dynamic programming is an optimization method that works for a certain class of problems, like this problem, like the seam carving problem in your lab. It only works for some problems, but when it works, it's very fast. And it's basically just memoizing the recursive thing that we just looked at. So it has a fancy name, but intuitively, all we're going to do is what we just did, but remembering the answers as we do them so that we don't keep doing things over and over again. And we're going to be storing our intermediate results in an array so that we remember what we did. So there's a lot of applications: DNA sequence alignment, text hyphenation, certain machine learning models that you'll talk about later in the program, and the things we're doing in lecture and lab this week. And the name dynamic programming has no particular meaning. It's just a fancy name. Okay, so here it is. Okay, we'll not go into this code in detail at this moment, but at the very least, it's not like a million lines of code. And it's not recursive, it's a loop. And even before we look into the code, we can pretty much see the time and space complexity of this by just kind of reading off the code. So it looks like m and n are the length of x and the length of y, respectively. And I'm just doing loops for I in range pretty much m and n. So we can read off the time complexity as being the length of x times the length of y, more or less. And we can read off the space complexity, in fact, as being the same thing, because this is this array we're storing, which is roughly the length of x by length of y array. And so this is extremely promising compared to what we had before, because length of x times length of y is not going to be that bad compared to the 2 to the power of stuff that we were dealing with the recursive solution. So let me first run the code. Okay, it seems to get the same results. And let's talk about how it works, and then look at the code at the same time. So the recursive implementation, we could call it like top-down. It started at the top, find me the number of highlights between this string and that string, and it called it for the shorter strings and shorter strings and shorter strings, and we got this whole tree of recursion. And this sort of works the other way around. It starts with the small problems, so just the beginnings of the strings, and sort of builds up one on top of the other to get the entire solution. So basically, we have a 2D array we called it opt, and here's the key insight here. The ijth entry of my two-dimensional array stores the answer, the number of highlights, number of diffs, of these substrings. The first I characters of x and the first j characters of y. And so we can start with the beginning, like, well, the first 1 character of x and the first 1 character of y. Yeah, we can figure that out pretty easily. Either they're the same or not the same. We can just record the result being the number of highlights. But the thing is, from each entry here, we can get the next one. So let's say we want to compute opt ij. So we want to compute the number of highlights between x up to character I and y up to character j. Well, we can look at those two characters, and if those two characters are the same, and maybe I should go with this example. So let me get a blue. So let's say we want to compute just this subproblem. So ij is I is 3 and j is 3, so we just want to compute the thing up to here, but we've already done it for all the shorter strings. So what we can do is we can say, well, in this case, the current character c is the same. So if the current character c is the same, then there's no highlighting that needs to be done here. So basically, the number of highlights is the same as in the previous problem, because we've just added the same character to both, and so we do not have to pay any extra cost. So here, opt ij is equal to opt I minus 1, j minus 1, which is the solution to the subproblem with the shorter strings. So that's reflected in the code right here. Okay, maybe I got my indexing slightly off, but if you have the same character, then you just grab the previous answer. And then you have this other case. If they are not equal, then there's two possibilities. So now, let's say I'm now moving on to this part. I want to get entry 4, 4. Well, these characters are not equal. So I have two possibilities like we talked about. Should I highlight the D or should I highlight the H? And we know, because we've just been talking about it and we've looked at the whole strings, that highlighting the H is the better thing to do. So we have these two possibilities, but the thing is we've already computed the optimal highlights for those subproblems. So what happens if we highlight H and what happens if we highlight D? We've already built up to the optimal solution to that problem because those are already in our array. And so we have this. If they're different, the current answer is either I minus 1 j, which means that's highlighting, that's one option of highlighting because it's the subproblem between this and this, or I could have the subproblem between this and this. So basically I have two options. I could highlight the first string, the character in the first string, or I could highlight in the second string. But I've previously already computed the optimal solutions to those, so I can just take the better of the two and then pay my extra cost of 1 for that extra highlight. Now I think, I was thinking about this. This is the type of thing that takes quite a while to sink in. So when I first learned this and I tried to code something like this up for the first time, I remember it taking me like an entire day to produce something like those 10 lines of code. And so it's something that takes a while to soak in. And I actually think, after having made this lecture and reflecting on it, I actually think the dynamic programming in lab is a little bit less confusing than the one here because you don't have all this aligning going on. It's a little more clear what your options are. So I would say when you're thinking through this, try to also think about the case in lab where you're building the seam and you essentially just have 3 options you can go to, but you already know the optimal seam energies up to the previous row, and then you're just saying, I'm going to add one more, so what's my best choice going to be? Ryan.
When you were comparing D and H, you said since they're not equal, we already did some previous work, so we kind of know what opt I minus 1 and those two are. What if we hadn't done the previous work yet? I'm not seeing where that previous work is.
Yeah, so Ryan's question is, we rely on this previous work, but what if I haven't done the previous work left? So this is where it gets a little mind-bending. So we have this loop over I. So basically, you're building this table. You're kind of doing a nested loop. So you're going first row, second row, third row. And so by the time you're at a given point, you've already done the whole previous row because of the way the loops are set up. So the I minus 1 part has already been done previously. And then the j minus 1 part is just the thing you just did because you're looping over j. But it's still a bit surprising that this actually works, but it's just kind of like reasoning through. It's kind of one of those things that it should work when you talk about it, but it's still surprising that it does work because, yeah, I have to decide if I should highlight this, if I should highlight that. I've solved those sub-problems, and so I'm just going to take the better one and then pay my cost for highlighting. Let me check on the time. Okay. I need to keep going because of time. I know we didn't have enough time to do this properly because this would probably take the whole lecture to really go through it. But let's keep it going. I de-emphasized this relative to last year. So the lab you're working on, the dynamic programming code is actually provided for you, and you have to provide the pulp code and the vectorization code. In previous years, it was the other way around. But I think in terms of skills you're likely to need, I think the vectorization is probably the most useful. And then this kind of thinking about encoding things as optimization problems is, in my opinion, maybe the next most useful. And some of you may have to implement dynamic programming from scratch, but in the most cases, you'll probably be using packages that use dynamic programming under the hood. So let's keep going. Okay, so I also have a part of my code that prints out this table that I was talking about that we were building. And again, this is the table of the number of highlights between the subproblems. So the first I characters of X being matched with the first J characters of Y. And so you could see, for example, here, this is 6 because you're basically matching none of X with all of Y, and so it just has to highlight all of Y, which is 6 characters long, and so you pay this cost of 6. And here you're doing none of Y with all of X, and so you have to delete all those 7 characters of X, since you have a 7 here. So you get this sort of 1, 2, 3, 4, 5, 6, 7 along the top and the left, because you're matching basically an empty string with part of the other string. And then you go through and fill these things in along the way, looking at the previous case. And what you get to at the end, the bottom right, is the entire X with the entire Y, and that's actually the answer that the code outputs. So I just wanted to show you that if I call this recursive function that we talked about earlier, and I literally pass in the substring, so I literally pass in a subset of X and a subset of Y and call that recursive code that is a lot easier to understand, that you get the same table. So I'm just kind of manually building this table with the recursive code just to show it really is getting the scores from the subproblems, but in this faster way. Yes, Tom?
Sorry, can you quickly go over one more time how to read the table?
Yes, how to read the table. So the ijth entry of the table is the number of highlights, or the objective, or the score, or whatever you want to call it, between the first I characters of X and the first J characters of Y. So, for example, so you can see that here. The ijth entry of the table comes from the score between the first I characters of X and the first J characters of Y. So, for example, this thing up here, which is 1, 2, 3, 4, 5, position 6, 2, or whatever that is the first 6 characters of X with the first 2 characters of Y. And if you compare those, then you need 3 highlights. So you will be building a similar table in the lab, which is the minimum amount of energy to get from the top of your image to a particular pixel. And that's going to be the equivalent table in your lab.
Sorry, how did you come to the number 3 to be your answer, or?
Well, in this case, I literally just computed it directly by saying I'll just take those substrings and use the recursive solution just to verify that that's what the dynamic programming is doing. But the dynamic programming is not So the recursive code is basically recomputing each of these numbers from scratch, and the dynamic programming is saying I can actually get this number from this number 3, I can get it from the previous two numbers, because the thing from above is like I'm adding a character to x, and the thing from the left is I'm adding a character to y, and so I can update the scores that way. Okay, here we go. So the next thing we need to do with dynamic programming is we need to actually, we don't just want to get the score, but we actually want to recover which characters were highlighted. So in order to do that, we need to do something that's called backtracking in dynamic programming, which is essentially looking through this table and trying to figure out where we came from. And again, you'll be doing the same thing, or I guess the code is provided to you, but the same thing happens in the lab. So, for example, if the score here is 3, then you want to figure out, well, did I get to this 3 by highlighting the character in X, or highlighting the character in Y, or matching, or were they just the same and I didn't need to highlight any of them? Okay, so I have the code for that here as well. And it's a bit of a mess because I wanted to get fancy and include the actual highlighting in the code. But let me just run the code. So again, yeah, I got fancy with the highlighting and made it actually output the highlighted stuff. Again, we have not enough time to go through the code in detail, so you can ask me about it later, but I have it here for you to look through, and it's essentially starting at the end and going backwards and trying to figure out which thing was highlighted based on those scores. Okay, so one thing I wanted to point out to you is that this was the thing I screenshotted from GitHub, and this was my code over here. And you can see the highlighting is actually slightly different. So my code highlighted these first 3 spaces, and GitHub highlighted these second, third, and fourth spaces. And that's an example of something we talked about over here, that the solution is actually not unique. So both of those are totally valid, and they both have the same number of highlighted characters, 10, and so it's kind of arbitrary whether your code is going to return one of those highlights or the other. Okay, it's getting late, so why don't we take our break now? We'll resume at 10:22, and then we can go on to vectorization. I'm going to try to change course a little bit and forget about the lack of time. We'll maybe skip the optional things or breeze through them, but I want to go through this a bit more slowly because I think it wasn't clearly explained. So let's go through this example, which is where this table came from. So how do we get all those numbers? Well, we start with this 0, 0 up here. That 0, 0 is supposed to be the best score for matching the first 0 elements of x to the first 0 elements of y. So there's just a nothing with a nothing. So the number of highlights is 0. So that's where this 0 comes from. Now we move on, because we're looping through, as we talked about with Ryan. We're looping over I and j. So the next element we need to fill into the table as we're going through is this 1. What does that element in the table represent? It represents position 0, 1. So it represents matching the first 0 characters of x with the first 1 character of y. That is going to cost you 1 highlight because, well, you're going to have to highlight this h. Maybe I'll write this a bit bigger too. If I need to match the first 0 characters of x with the first character of y, then, well, I just have to highlight that H because it's a new H. I started with nothing, and now I have an H. And that's how we get this 0, 1, 2, 3, 4, 5, 6. Because I can match nothing of X with HE, that's going to be 2 highlights. I can match nothing in X with HEL, that's 3 highlights, etc., etc. So in the code, these things are just filled in automatically. They're always going to be 0, 1, 2, 3, 4, etc., etc. And same thing going down. So going down, for example, this one here says match the first 1 element of X with 0 elements of Y. So match this X with nothing. Well, I just deleted the X, so I have 1 highlight. Same. Match the first 2 elements of X with 0 elements of Y. I just deleted those 2 X's, so I have to highlight them, so that's 2. So I get the same 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, 7. So first, any questions about where those numbers come from? Yes, go ahead.
We just initialized the array with m+1 and n+1 because you wanted to have a 0-length character.
Yes, the size of the array is 1 larger than the size of the string because I'm going from 0 characters to all the characters, yes. Okay, so the next question is, now I'm going through my loop, right? And then I have to fill in this 2. So to fill in this 2, that's saying match the first character of X with the first character of Y. That's what that position means. So I'm solving the subproblem of aligning X with H. And so here's the reasoning behind this. Well, I have to align X with H, and that could have come from 2 possible places. It could have come from the fact that I first deleted X, and so I was aligning things. So I had already highlighted X, and by the way, already highlighted X means this thing over here. It means I took the first character of X and I deleted it. Or it could have happened that I already highlighted H, and that's this one over here. So, in other words, I could have matched the first 0 characters of X with the first 1 character of Y, or the first 1 character of X with the first 0 characters of Y. And now I want to match the first 1 character of X with the first 1 character of Y. And so I'm going to look and say, well, I could have come from those 2 possible places. I could have come from X was already highlighted and I haven't decided what to do with Y yet, or Y is already highlighted and I haven't decided what to do with X yet. Which one of those is better? And that's where that minimum comes in the code. You take the minimum of your neighbor above and your neighbor to the left. So it's saying, well, those both cost me 1. So actually, in this case, I don't care. I'm just going to take, the minimum is 1 either way. And then I'm going to pay this extra cost because these don't match. And that's why I have a 2 in there. So what that's saying is now where I'm at is that the best possible alignment of the first character here and the first character here is just highlighting both of them. And we already know that, that's obvious. I mean, X and H are different, so yes, we have to highlight both of them, and that's why we have a score of 2. But we actually came at it from 2 possible angles. Highlight this and then highlight that, or highlight that and then highlight this. And here it's not very interesting because they're the same. But let's try to take a case that is more interesting. So here's, for example, entry 0, 1, 2, 3, 4, comma 1. So the first 4 characters of X with the first 1 character of Y. Okay, so we want to highlight 3. Okay, so we want to highlight the first 4 characters of X with the first 1 character of Y. And so we say, well, again, we could have came at this from 2 places. We could have came at this from our previous highlighting was we had aligned the first 3 characters of X with the first character of Y. That's coming at it from the left. Sorry, that's coming at it from above. First 3 characters of X with the first character of Y. That's coming at it from above. And that's actually the better alignment here because X, X, H compared with just H there's only two differences. There's only those two x's that need to be highlighted. And so that's that score of 2 coming from above. If you think about it as coming at it from xxh versus just h, well, there's only two highlights that need to be made there. Xx, and so now I'm going to, the h's match, and then I'm going to have to highlight the e, and that's going to give me my score of 3. Versus, I could have come at it the other way, from the left, which is highlighting, which is aligning all of these 4 characters of x with nothing, basically assuming these are all deletions, deletion, 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 deletion. And in that case, I would have already paid a penalty of 4, and now I'm paying 1 extra penalty for my new highlight, and now I'm paying a penalty of 5. So it's basically saying, to get the best solution to the subproblem, the first 4 characters of x with the first 1 character of y, would it have been better to come at it from this angle, where x is deleted, and h is matching, or would it be better to come at it from the other angle, where x, h, e are all deleted? But because you've already solved those previous subproblems, you have those scores just sitting there. The score is 2 from the one approach, and the score is 4 from the other approach. So you can just take the better one, because it had to be one of those 2 alignments. And then the 2 is better than the 4, so you take the 2, and then you add 1 more to the 2, and that gives you your 3. Yes, Derek?
Is this like binary decision making, but you're saving your choice in a matrix kind of?
Yes, I think that's a fair way of putting it. It's binary decision making, but you're saving your choice in a matrix. You're saving not actually the choice, but the score,
Right.
assuming you made the best choice. Because the thing is, by the time you're matching this string to that string, like now you've gotten back to the same place, whether you've gone delete, 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 add, or delete, delete, match, add. Now you're kind of back at the same place again. So you might as well take the better of the 2, which is match the h. Because going forward, you're back at the same place, right? You're back at the best solution of the first 4 of these with the best one of these. So you only want the best one. Rob?
Yeah, so it is saying that once we have the first row and the first column, we get the whole matrix?
Yes, once you have the first row and the first column, you can get the whole matrix, and furthermore, the first row and the first column you can just hard code. So you can just, they're always going to be those things because it's comparing an empty string against a bunch of stuff, which is just all going to be that many insertions, or comparing a string against an empty string, which is going to be that many deletions. So no matter what happens, the top row is always going to be 0, 1, 2, 3, 4, 5, 6, and the left column is also going to be 0, 1, 2, 3, 4, 5, 6, 7. And so then you can start filling in everything else one at a time, because it only relies on the stuff up and to the left of it.
Then basically this matrix has nothing to do with exactly the strings are?
The matrix does have to do with what the strings are, because position ij in the matrix, like here, is the best possible alignment of the first 1 characters of x and the first 1 characters of y. So this 2 here says the best thing you can do with the first character of x and the first character of y, in this case they don't match, so the best thing you can do is highlight both of them, and that's a penalty of 2, which is why you have a 2 there. So it's true that the first row and the first column of the matrix have nothing to do with x and y, but all the rest of the matrix does come from the particular strings that you're trying to match. Sam?
Well, I was following, but then I looked down the matrix at the bottom right, and there's the 2 and then the 3.
Yeah?
So the 2 has a 3 above it and a 3 to the left of it. So how do we get a better score there?
Right. Haha, great question, Sam. So the 2 has a 3 above it and the 3 to the left of it. How did we get something lower? So it actually came from here. So basically, to get from this 2 to that 2, you have a path that you could insert and then delete and then insert. But since they happen to be the same character, I think it's maybe the O and the O, they match. So you actually hop diagonally from... It's saying this. You know that this substring to this substring is a 2. That's the 2 I've highlighted. And now you want to go one longer in X and one longer in Y. Well, since there's a match, there's no extra penalty there. So you could just copy that too. If you can match this blue thing and this blue thing with only 2 highlights, which we know you can, these 2 highlights, then you must be able to match this and this with only 2 highlights because that letter is the same. And so that's what we have in the code. Let me go back up to the code. We say if the characters actually match, you can just hop diagonally. And if they don't, then you have to either come from above or from the left. Evelyn.
Just on that, so the idea, since they're both 3s, is basically that's what's saying if they match. That's kind of like equivalent values surrounding that too. It's like a way of thinking if they both match.
It's not that these 3s match each other, it's that the characters match each other. So this code is looking at the strings themselves and looking at the other numbers.
Okay, so it's not like a hack you could use interpreting the table.
Not really, but it's fine, because the code needs to look at the data itself and at the other stuff in the table. Right.
What exactly now this qualifies this as dynamic programming? Like,
what exactly qualifies this as dynamic programming? It's essentially a fact that you have a recursive solution and you can remember optimal solutions to subproblems. So it's kind of like that with the seam carving as well. Like you can get to a particular pixel from a lot of different seams, but this is the optimal way to get to this pixel, and then you just keep going from there. So that's like the subproblem is getting a seam up to that pixel.
so it's using that cache decorator, that form of dynamic programming?
I don't know, that's debatable. I mean, not really. I guess you would call that caching, and you would call this dynamic programming because you explicitly laid it all out. Tom?
Just so in our example with the X and hello, all you've done essentially has moved that hello. You shifted that hello.
Yeah.
What happens if you change like a character, so like an E to the E in it to an O? Does that count as 2?
Yeah, so if you change a character, it's going to end up being an insertion and a deletion. And it'll say, oh, I could insert and then delete, or I could delete and then insert, and it'll take the minimum of those two, say, well, they're equally good, so it'll arbitrarily pick one and then pay the price.
Thank you.
Okay, let's move on. That was a bit rough, but maybe this extra thing was better than not doing it. I don't know. Okay, we need to keep going. Talk about vectorization. Whew. What am I going to do? Okay, so vectorization. Here is a 10 million length arrays, and what I'm doing here is I'm just adding 1 to each element of X. And this took 6 seconds. And now what I'm doing instead with NumPy is I'm making an array of zeros of that same size, 10 million, and I'm adding it like this, and it's 5,000 times faster or something like that. So both of those are O of n operations. One is doing a loop, and one is doing just a sum, but they're giving me the same answers, and one is way faster than the other. So the question is, how is this possible? And this is called vectorization, and it's this weird thing that says, most of this course has been talking about better algorithms, better data structures, better big O. But in this case, the big O is exactly the same. It's just different code that's doing the exact same steps in a much more optimized way. So basically, it says that NumPy is very good at doing things really fast. So here in Python, because it's a loop, what Python is really doing is Python is kind of living in the moment and just going one step at a time in the loop. Oh, I'm supposed to add 1 to this number, great, maybe I'll take a 5-minute break. Oh, I'm supposed to add 1 to this number, great, maybe I'll take a 5-minute break. Whereas, because it's basically executing each of those things in the loop one at a time. On the other hand, when you do this, when Python sees that one line of code, it immediately, because it's looking one line of code at a time essentially, it's immediately saying, oh, this person wants to add 1 to every single number in this giant array. Let me do some super optimized thing that's really fast at adding 1 to a whole bunch of numbers. Because basically it knows in advance when it reads that line of code that it's about to add 1 to a ton of numbers. because that's what that line of code means. Whereas in the loop, it's not really looking ahead and saying, oh, I'm about to loop through a ton of numbers and add one to them. It's just saying, I'll just take things one step at a time. And I'm not really going to go into the code optimizations that make this super fast, but that's the general idea of why it's so fast. So I want to do a case study of distances. So here I've created just two random vectors of length 100. And I'm just computing the Euclidean distance between them, meaning subtract all the elements, square them, and add them all up. Okay, so here's what I can do. X minus y, that's vectorized in NumPy. Square it, that's vectorized in NumPy. And then sum, that's all going to go really fast. And now the question is, what if I want to do this for a bunch of pairs of x and y vectors? So I have 5 different x vectors, 3 different y vectors, and I want to find the distances between all pairs. So I have 15 distances to do with x1 and y1, x1 and y2, x1 and y3, x2 and y1, etc. So here's what I can do. I can just make a loop that says, okay, my squared distances are going to go in this array. I make the array, and then I'm looping over the number of x vectors I have. I'm looping over the number of y vectors I have. Oops. And then I'm just saying, calling that code we just saw above. I'm taking my x vector, my y vector, and storing it in the array. Okay, so that works. Now I have 15 distances between these random vectors that I generated. And I'll just put this in a function so we can time it. Okay, so I have 1,000 x vectors, 1,000 y vectors, each is of length 100, and I can just time how long this takes. And it takes 8 seconds, and this already seems pretty bad, pretty good. I mean, I used np.sum, that should be vectorized, that's great, but I still had those 2 nested loops in there. And the running time of this is O of d, that's the length of the vector, so 100 elements in each, times the number of x vectors times the number of y vectors. And so I don't really have time now because I've ran out of time, but you can use broadcasting, which was covered in the wrangling course. So Tom talked to you about broadcasting, about lining things up. And so you can actually use broadcasting to basically do those entire nested loops in one line. And take a look at how fast this is. So first of all, I'll show you they give you the same answer, but this took 1 second as opposed to around 7 or 8 seconds. So this is the kind of thing where it's like, I think I'm already doing a good job. I'm maybe already using np.sum, but you can actually replace even more loops with broadcasting, and 5 times faster can make a big difference. I mean, if your code is going to take 5 hours to run versus 1 hour to run, that could make a big difference for you. So too short on time to really pick apart this code and understand what it's doing, but I at least want to show you that vectorization can really speed things up a lot. And that's what you're going to see in the last part of your lab, is that you already use dynamic programming, you're feeling so good about yourself, but then you can even make it like 5 or 10 times faster just by getting rid of some loops and doing some clever NumPy stuff. And it's quite surprising what big of a difference it makes. Okay, so I'm going to skip some of this, but if you're interested, read through this. There's some very clever algorithms that can make it even faster. And basically what I just want to talk about is why and when can you vectorize your code. So if you're doing some sort of algorithm where the current step really depends on the previous step, you can't really vectorize your code. So for example, if we were doing those stock simulations in 511 and each stock price depended on the previous stock price, you really need to know what that previous value is going to be to get the next value. So you pretty much have to use a loop there. You have to get the next one, the next one, the next one. But vectorization works when you could do all of those things at once. And then there's often a clever way in NumPy to make the code run faster. So this brings up an important general theme here, which is that there's two distinct avenues to speed up your code when your code is too slow. You can come up with faster algorithms, like we talked about dynamic programming or breadth for search or whatever. You might have a better algorithm or data structure that say, hey, if I use that, my big O is actually going to be a lot smaller, and so that's going to make my code faster. But there's this whole other category of ways to make your code faster, which is the big O is exactly the same. I'm just using better code to make things faster. And so I'm using some super optimized thing that it's really the same number of operations, but each operation is much faster. And that's this better implementation thing. And sometimes you'll have to resort to that. Sometimes you may even have to abandon the programming language you're using and go to a different programming language, write the exact same code, and it'll just be faster because that's a faster programming language, which is frustrating, but and is happening less and less these days as our computing infrastructure gets better. But I just wanted to point out this other avenue, and that's what you'll see on the lab. You use a better algorithm, then you use dynamic programming in the lab. You're not going to find a better algorithm than that, but then you get a better implementation and your code gets even faster. So I don't have time for these optional things. I recommend you look through them later. So profiling, snake viz, doesn't matter, don't have time anyway. Profiling is a tool that allows you to look inside of your code and see which parts of it are slow and which parts of it are fast. Wasn't getting an error. Oh, I just didn't define my functions. Sorry. Didn't run the earlier code. Anyways, profiling is a tool that can visually show you which parts of your code are fast and slow.
I don't think there's a function called pairwise distances.
What's it called? Squared?
Pairwise squared distances broadcast. Pairwise, yeah, squared distances broadcast.
Thanks. Okay, yeah, so this is like a fancy visualization tool that you can basically dig into your code, and it'll tell you what lines of your code are fast and slow and all this stuff. That's really impressive. So you may want to take into that. If you're like, my code is slow, but I don't know which line of code or why it's slow, you can try these profilers, which will visually show you what parts of your code are slow. If you're interested in this, you can look through it. There's various tools that basically make Python faster. So again, there's more of these decorators that we saw earlier. You can sometimes just add a little thing to the top of your function and it'll go way faster. So there's Numba, Cython, PyPy, all these tools that you don't necessarily need to look into them right now, but you should know they exist, because if you're really hitting a wall with your code being too slow, you may want to go back and say, hey, there might be some fancy thing I can do within Python before I abandon Python entirely. There's parallelization, so your laptop may have 8 cores and you're just using one of them to do your computation, and there are Python packages that can say, do stuff on all 8 cores, and if you're lucky, it'll be 8 times faster. And so there are Python packages for that you can look into. Again, if you're interested, this is all optional. And now we have 1 minute for the course wrap-up. So the goals of the course, I just want to go through them and talk about what we did. So analyze the scalability and trade-offs of various algorithms and data structures using big O notation. Read and interpret recursive functions, select appropriate data structures such as graphs, map real-world problems to optimization problems, and determine rate-limiting aspects of slow Python code, and enumerate various options of speeding things up. So we did a ton of stuff in this course. For those of you who are coming into this having never seen, say, big O notation before, which is probably a lot of you, you should be proud, because we've just done a huge amount of topics. and hopefully they will be useful to you going forward, and maybe there's some kind of new ways of thinking that have been opened up as a result of this course. So great job.